go. Right, so here we go. In a simple model, the population of a bacteria, the growth rate is assumed to be proportional to the number of bacteria. And then it goes here, let n be the number of bacteria after t minutes. Initially there are 2,000 bacteria, and the number increases to 10,000 after 12 minutes. So you've got two conditions there. Write and solve a differential equation to find the number of bacteria after t minutes. Now, let's just have a look at this. It tells me that a simple model, population of bacteria, the growth rate. So let's look at the growth rate. Growth rate is dn, the way the population is changing. The rate is always in terms of dt. We've said that before, how we do with this. So that's the growth rate, and it's proportional to, proportional to the number of bacteria. Now before I start this, because we link it up like GCSE, when you say proportional, you should really use this symbol, proportional to the number of bacteria, which is n. We're calling that n. So growth rate is proportional to n. Now you will taught a little stunt at GCSE. How can you replace the proportional sign? You have to introduce a k. Okay, so dn dt equals kn. Okay, happy days. Now I'm going to start. Now I've got this. Sometimes in the exam it might say show this, and you got a mark or two to set this up, and then you work forward. But now it's told you that initially means t equals 0. There are n is 2,000. So I'm going to quickly just write that down, and then I'm going to break this down and differentiate it. So I'm going to separate my n's, bring my n to this side, 1 over n dn. I'm going to leave the k on this side, which you should do, and bring the t there. Integrate both sides. So we all know that the integral of 1 over n is just going to be a natural log of n, and that's going to be kt plus c. Right, what I'm going to do is I'm going to bring this, I'm going to bring this here. I'm going to write this here, so just put a box around it. So I'm going to rewrite that. I'm going to write it here. So I know that, and this time I'm going to plug these numbers in. When n equals 2,000, t is 0, so that gets rid of that. So that goes, and c is equal to ln of 2,000. So now you can write ln of n is equal to kt add ln of 2,000. Now there's a reason they gave you two conditions, because you had two unknowns. You had this constant here, c, and you have this k here. So that's got rid of one condition. Let's look at the other condition. Now in here we also been told that, I'm going to write it here, when t is 12 minutes, the population size is 10,000. So now I'm going to plug that condition in to get k out, hopefully. So let's put this in. That's going to give me ln of 10,000. K is 12, t is 12, so that's going to be 12k plus ln of 2,000. I'm going to take that to the other side, so I get ln of 10,000 minus ln of 2,000 equals 12k. Now you know that when you mine these logs, it's a division, so that becomes ln of 10,000 divided by 2,000 equals 12k. 10,000 divided by 2,000 is 5, so that is ln of 5. And that is 12k. Divide that by 12 gives me 112. ln of 5 equals k. Now that's lovely. I can go and plug that back in here because I know what k is now, and rewrite this as ln of capital N equals 1/12 ln of 5 times t plus ln of 2000. Now, we're almost there, but we want to solve the equation to find number of bacteria after t minutes. So we want it in terms of n, excellent. So we just need to get rid of the e. So get rid of the ln, so I'm gonna e both sides. So put a big bracket here and e both sides. So if I e that, e and n over e, they cancel each other out. So I'm just gonna get n equals e to the power 1/12 ln of 5 times t dot e to the ln of 2000. Now note that I wrote that, you could jump straight into it and put the 2000, but I wrote there so you can see that will cancel each other. So you end with 2000 e times e to the power 1/12 ln of 5t. Now, that is it. That is it. Now, what it says here, comment on the limitation of this model. Now, if you look at this, it's a positive power ln, and as t increases, the e will also increase. In fact, it will start increasing exponentially. So the limitation here, what it's telling you is the population will keep on growing exponentially, which can't be true. Okay, so that's the limitation this model predicts. The population is forever increasing, which in reality, if we think about fishes in a pond, you can only have so much fishes in a pond, otherwise it just gets overpopulated and things will start dying off. Okie dokie.